Problem with using Hamiltonian cycles to find one factors is that there isn't really a good way to find Hamiltonian cycles except through brute force. So I don't really want to use this as a condition. But back in chapter 6, where we were talking about Hamiltonian cycles, we did have a theorem about components. So let's suppose we have a Hamiltonian graph which has even order. Then I can think about whether or not I'll have a one factor, because if it has odd order, we're screwed. Pick a non-empty subset of vertices. I pull away this set. Assuming not all of the vertices, I'm left with some, right? I'm left with some components. Back in chapter 6, we said this. What's that mean? That's a regular lowercase k, not the fancy k. I will end up with fewer components than the number of things I took away. Makes sense. If it's Hamiltonian, then I can get from any vertex to any other. So if I take away one, I won't disconnect. If I take away two, I might break the cycle, I might not. Even if I broke the cycle. But that's if it's Hamiltonian, then this is true. We know that the converse of this is not true, using the Peterson graph as a counterexample. Because we know the Peterson graph is not Hamiltonian. On Wednesday, we looked at a graph that had a cut vertex. When I pulled that cut vertex, I was stuck with three components, right? So the number of components is bigger than the size of the set of vertices I remove. But what's worse is that none of those other components had even order. So I want to actually take this idea and split it into two pieces. When I talk about the resulting components after removing some vertices, I want to decide if those components are odd or even. So consider the number of vertices in a component as if it was a separate subgraph of G. And then if that number is odd, we have an odd component. If that number is even, we have an even component. And I'm going to call K0 of G, well, KO, let's use O for odd. And it turns out this tweak is enough. Instead of just looking at all the components, only look at the odd ones. If I take away any set of vertices and the number of odd components is less than the number of vertices I took away, then I have a one factor. Half of this proof is easy, half of this proof sucks. I'm only going to do the easy half. So if I have a one factor, I have a perfect matching. Let's call this one factor F. By definition, F is a fixed number of copies of P1, two vertices with one edge between them, that spans the vertices of G. So take some vertices. And let's take them away. Now there are some options here. I'm going to look at the resulting components of G minus S. And since I have no idea how many vertices we took away, all I want to know is whether or not there are any odd components. Because my goal is to show that the number of odd components is less than or equal to the number of vertices I took away. But clearly, if there are no odd components, yay, 0 is less than whatever I took away. That was easy. If we have any odd components, we're going to have some of them, right? I don't know how many. There could be a bunch of odd components and some even components too. I really don't care about the even components, but let me label the odd components. I don't know how many there are, so I'll call it K, but I know K is at least one. I'll call the subcomponents G1 through GK. Huh. Each of those are odd, right? Each of those are odd components. I have another subgraph, right? How does F interact with these components? F is a bunch of copies of one edge, two vertices. Yes? The order of GI is odd. At least one vertex in GI had to be connected in F to some vertex in the set I took away. Otherwise, there would be an even number of vertices in that component because I have a perfect matching within that component. I'm not F, S. Hey, wait a minute. I only took away the vertices in S, right? Every odd component has to touch something in S. The total number of odd components can't be more than S. Why can't it touch two things in S? Because that's a perfect matching. And it only goes to one other thing. The other half of this proof is a two-page induction argument. It's mostly worth reading because the neat idea is to figure out how to build the one factor from those odd components. Interestingly enough, this result, this theorem, is known as Tutt's theorem. Tut was a chemist. Studied graph theory as chemical molecular models. So here's a stretch and a half. 2D flat graph theory models. Every chemistry book in the universe, right? You draw all these they're graph theory designs. Why is he looking for one factors in chemical models? He's looking for single bonds, which are easier to break and liberate energy from. Pharmaceutical chemistry via graph theory. He eventually went on to do a lot of mathematics, not just this little bit in this one place. Tut was a very interesting mathematician. Page 197, there's a very interesting little biographical sketch. Questions? Our drawn pictures, page 195, of the ones that have one factors and the one that doesn't, all of those upper graphs have one factors. The first two in the second row and the Peterson graph have a criteria that the second two in that bottom row don't have. How are these two different than these three? Bridges. So being bridgeless is an interesting indicator. And it turns out that there is a connection to being bridgeless and having a one factor. And it was actually Peterson who discovered this. And he discovered this before Tut, but Tut's theorem actually makes the proof easier. Peterson says every bridgeless three regular graph has a one factor. There was another word for three regular. What's the other word we used for three regular? It was. I want to do this proof using Tut's theorem. So I want to take away a set of vertices and prove that the number of odd components is less than what I took away. So I have a three regular bridgeless graph. Cubic, bridgeless. Are any of the ones in our picture cubic? Go back to page 195 and see if any of those are cubic So I use them at least mentally as examples. Wait a minute, the Peterson graph is cubic. So I use the Peterson graph as my example. As a matter of fact, look carefully. Tell me the degree of any vertex anywhere on that page. They're all cubic. So these three are cubic and bridgeless. These three are cubics with bridges. So we can talk about any of these as the example in our head. So when I say a cubic bridgeless graph, you can picture the Peterson graph or this or the K33 here. I need to know how many vertices I'm taking away. So let's give that a name. The size of S will be K, bigger than or equal to 1. So I'm taking away at least one vertex. If K naught G minus S equals 0, we are done. Why? S is just a subset of vertices. It could be proper, but that's not required by what we wrote down here. I took away at least one vertex, and 0 is smaller than 1. Poof. That's it. Remember, my goal is to show that the number of odd components is less than the number of vertices I took away. I took away at least one. So suppose I do have odd components. Let's number them G1 through GL. I already used K. I don't want to use it again. Is that in this picture? When we looked at a one factor, we said, oh, it's got to connect to these components somehow, right? I don't have a one factor yet. I'm trying to build one, or at least show that I have fewer components to know that I will get a one factor. So let xi be a set of edges. Not just any set of edges, the set of edges connecting each of those odd components to vertices in S. Time for some counting arguments. What do you know about every vertex in this entire graph? The degree is 3. I also know GI is a component, right? Total sum of the degrees must be even. Wait a minute. What does that tell me about the number of edges I took away? Let's just look at G1. G1 is an odd component, which means it has an odd number of vertices. But every vertex had degree 3 in the original graph. I had to take away to end up with an even number. Not necessarily, but at least an odd number, right? Maybe it's 1. How do I know it's not 1? Hint, it's another condition required by my graph. And if there was only one thing taken away to disconnect, I must have had a bridge, right? I have to take away at least 2 things to disconnect without a bridge, but I had to take away an odd number of things, so it can't be 1. It's got to be at least 3, Abigail. Hey, wait a minute. G1 through GL, right? There were L odd components. I had to have taken away at least 3 edges each time. Why do I say at least there? It would help if I actually wrote down the words at least. If I didn't say it, you can't answer why I said it. I counted the edges connecting GI to S. Why could there be other edges? Connected to S. I've only counted edges that are connected to odd components. There could also be even components, couldn't there? And that means there are 3L edges joining the GIs, vertices in S to the vertices of G minus S. But there could also be edges going off to the even components. I didn't even look at those. But order of S equals K. What do you know about every one of those K vertices? What do you know about every vertex in the entire graph? They're all of degree 3. Okay, wait a minute. That means there are at most 3K edges. K vertices, all of degree 3. Maybe they all connect to S, with every edge that comes out of the vertex in S. Sorry, in G minus S. Wait a minute. At least 3L, but at most 3K. That means that 3L is smaller than 3K. Well, it could be equal, right? What was L again? What the L? The number of odd components is less than or equal to the number of vertices we took away. By Tutt's theorem, I have a 1 factor. I've just satisfied the condition of Tutt's theorem. Okay. The graphs we have in that picture on page 195, some of them have bridges, but still have 1 factors. So Peterson only managed to show this for bridgeless graphs. Turns out we can have some bridges. The bottom graph on page 195 has 3 bridges. That's the one that's hooked up. Guess what our strict limit is? Our sharp bound on the number of bridges that are okay. Now, there's an awful lot of study about graphs that is particular to cubic graphs because they occur a lot where Tut was working in chemistry. A lot of molecular structures turn out to be three-regular. Surprise. So let's consider a cubic graph. Any of the ones in that top diagram with two or fewer bridges has a one factor. So let's say we have a one factor. I'll even call it F1, a one factor. What happens if I take those edges away? What do you know about that graph? I need to fill in the adjective that comes after the word is. Take any of the pictures on page 195 in that top group of 5, pull out a one factor. Take the Peterson graph. What was our obvious one factor in the Peterson graph? Outer to inner. You take away the outer to inner, what are you left with? The inside star and the outside pentagon. What's every degree? It's two regular. You have a perfect matching. So each vertex has an edge from A to B. I remove that one edge. I'm left with every vertex now dropping in degree by 1. Well, now I can ask the question about the new graph. Is the new graph that we just built going to contain a one factor or not? Maybe, maybe not, right? It's too regular. What do we know about two regular graphs? Not just contain, they are cycles. Maybe more than one, like the Peterson graph, right? It's the outside pentagon and it's the inside star, which is still a cycle. You just have to unfold the star part of it. That's the complement of the pentagon in K5. Oh, but C5 can't contain a one factor. Why? Odd. But some of the other graphs I drew, maybe when I take them out, the resulting pieces are even. Maybe it's not true in the Peterson graph, but maybe I take away the one factor and I'm left with a C10 instead of two C5s, right? Well, then I could have a perfect matching. Hey, wait a second. If this has a one factor, F2, what if I take away those edges? What's that graph? And every one regular graph is a perfect matching in and of itself, isn't it? Which means if I have one factor in there, I've got cycles, I have to actually have two, right? So it turns out that it is possible to take a cubic graph and end up with three pairwise edge disjoint one factors. I'm able to classify every different edge in my graph. You belong to factor one, you belong to factor two, you belong to factor three. I factored my graph. I'm back to algebra class. A graph is one factorable if there exists a set of one factors in G so that the set of edges is a partition of the edge set of G. We have a one factorization of our graph. Now, for this to have happened, what do I know about G? Why? Every edge belongs to one and only one of those collections of edges. Every vertex has to appear in all of them. Because it's a one factor, it's got to cover all the vertices. So each edge, each vertex has to have one edge in each of those. G must be R regular. Okay, so every one factorable graph is regular. I don't know what regular it is. It might be 5 regular if it can be factored into 5 one factors. It might be 7 regular. It might be 3 regular. I don't know. Peterson's theorem guarantees me a one factor when G is bridgeless and cubic. But it doesn't guarantee me factorable. It just guarantees me a one factor. Now, I just said the Peterson graph itself, when I take away the one factor that's all the outside to inside, leaves me 2 cycles of size 5. Cycle of size 5 is an odd component. There's no one factor in it. What if I had a complete different one factor? What if I didn't use the outside to inside one factor? Might there be a way to factor this? Maybe the resulting thing would be better. Plain, the answer to that is no. Think about that. We'll talk more about that on Monday. See if you can come up with the why. And then we'll see what we can figure out about graphs that are one factorable and what to do with the ones that aren't.